So we were discussing about the torque slip characteristics of induction motor, and that we obtained it from the equivalent circuit calculations. And to begin with, we considered a very simple equivalent circuit neglecting the stator impedance. And in that case, the equivalent circuit will look like this one. When the machine operates at a particular slip S, and this is the per phase applied voltage to the machine, and this is the rotor deflected current, which will happen to be the stator current drawn under the conditions or assumptions that no load current is neglected. So with this one we obtained the torque slip characteristics in this way. It was like this. Just quickly I will review. This is S equal to 1 and this is S equal to 0, and this is the value of the torque. And the expression of the torque developed by the machine is given by this simple expression, S square plus alpha square, where K is given by 3V1 square by 2 pi ns into x2 dashed, if you remember. And also you remember that this slip at which maximum torque will occur is at S equal to alpha, and this is Tmax, or sometimes called the pull-out torque of the machine. Then also we explained which portion of the torque slip characteristics will be stable and which portion is unstable. That is, induction motor will never operate in this zone. This is unstable zone. So operating speed of an induction motor, strictly speaking, will vary between this to this. That is, between S equal to 0 to S equal to alpha. However, the machine at full load speed or slip is never chosen very close to S equal to alpha, because then it will be liable to cross this critical point and come to the unstable zone. Generally, the slip of the full load slip of the induction motor, say full load torque, is around say 5% or 4% like that. So a typical value could be 0.05. This is the full load slip. Okay. Now in this derivation we have neglected the stator impedance. Now suppose we want to refine this equation a little bit. Although this equation will be quite handy in explaining very basic things of induction motors, but still we derive that equation as well. Suppose stator impedance is considered. Stator impedance considered. In that case, the equivalent circuit per phase will be this way, R1 X1, and this will be the rotor deflected standstill leakage reactance per phase, and the rotor resistance per phase divided by S, and this is when the machine operates at a slip S, and this is the applied voltage per phase. And at this point the current drawn is suppose I2 dashed. Then once again I will repeat those steps so that you can understand. The torque developed, if you want to calculate, it should be equal to air gap power, you have to calculate, divided by synchronous speed, 2 pi ns. Now what is air gap power? Air gap power is the power involved in this resistance. This is the power which crosses the air gap and come to the rotor at this point, real power. So this will be 3 I2 dashed squared into R2 dashed by S, and whole divided by 2 pi ns. Now I2 dashed, obviously the magnitude of this current will be V1 divided by under root R1 plus R2 dashed by S whole squared plus x1 plus x2 dashed whole squared. So you just substitute this value here for I2 dashed to get electromagnetic torque developed by the machine as 3 b1 squared by 2 pi ns into, on the top it will be r2 dashed by s as usual, and divided by r1 plus r2 dashed by s whole squared plus x1 plus x2 dashed whole squared. So this will be the general expression of the torque of an induction motor whose stator impedances are also not neglected. Now here also, as a function of slip, if you calculate T and sketch these characteristics, it will be similar in nature. There will be a maximum value of torque like that. Now suppose you want to find out the slip at which maximum torque will develop. How will you do? How will you do? Suppose you want to calculate the slip at which maximum torque occurs. What you will do? You will differentiate and get the value of S, is not? But you can do it slightly in a different fashion, and you can get the result much more quickly. For example, in this case also, I calculate this S max by doing what? By differentiating this T with respect to S, is not? I differentiated, got the value of slip. Now, if you look at this circuit, for example, see, air gap power is a measure of torque developed, because it is only divided by a constant thing, that is 2 pi ns, that is synchronous speed, which is constant. So air gap power as it is a measure of torque developed by the machine, of course in wattage. That's why when torque is expressed in wattage, it is written as synchronous watt, that I told you earlier. Therefore, torque will be maximum when power in this resistance will be maximum. As simple as that, because that power divided by 2 pi ns will give you the maximum torque developed. Are you getting? So is it not? So the problem I know, I have to maximize the power. At what value of S power consumed in R2 dashed by S will be maximum? Tell me at what condition? When? See, it is a maximum power transfer theory problem. So under what condition? When the load impedance will become equal to the source impedance. That is, in this case, R2 dashed by S should be equal to X2 dashed. It is at that slip maximum power will be occurring at R2 dashed by S, hence maximum torque. So precisely that is what we got, which is nothing but alpha. Now here, of course, one can once again differentiate and get that thing, but tell me here, suppose we want to find out the slip at which maximum torque will be developed. So we have to maximize power here. So what will, at that slip, what will happen? At maximum power in R2 dashed by S. So this resistance you consider to be load resistance, and all other things you can include in the source side. So it is at that slip when R1 squared plus of x1 plus x2 dashed whole squared. It is this value of power. So whatever slip you will get, therefore the slip at which maximum torque occurs is given by R2 dashed over under root r1 square plus x2 dash squared. And what will be the value of maximum torque? T max. So you have to put this value of S in this expression. Is not? You have to put this value of S in this expression. In fact, S comes as R2 dashed by S. So I will put this value of R2 dashed by S here in this expression. So T max will be 3V1 squared by 2 pi ns into R2 dashed by S. R2 dashed by S is nothing but this quantity. And below you will be getting R1 plus R2 dashed by S, that is once again this quantity, R1 plus R2 dashed by S whole square plus X1 plus X2 dashed whole square. You can slightly simplify it so that you get it like this, 2 pi ns into this denominator. If you simplify a plus b whole square like that, so r1 square, there will be 2 r1 square. So this will be 2 r1 squared plus similarly 2 x1 plus x2 dashed whole square. This is square. A square plus b square. So this square and this square, 2. And then plus twice every term, 2a into under root of. This is elementary algebraic manipulation, nothing more than that. And this one will be like this. Now these two you can take out, 3v1 squared by some 4 pi ns it will become. And as you can see, you can divide the numerator, or you can take this factor common from below, or you divide this by numerator and denominator, this factor. So on the top it will become 1, and on the bottom it will be r1, this will yield r1, and this will yield root over r1 squared plus x1 plus x2 dashed whole square. So anyway, this will be the expression for T max. But what I will tell you that don't just remember or mark this up, because you know this basic thing, how to calculate the torque developed in an induction motor in this fashion. Are you getting? So like that you do. So this we know how to calculate therefore torque when even stator impedance is included. But what point I want to make is this slip at which the value of the maximum torque, you note here also it is independent. This point you make, the T max is independent of R2 dashed. The maximum value of torque does not depend on R2 dashed, which was also true in this case. The value of slip at which maximum torque occurs here, the value of maximum torque here will be how much? T max in this case will be how much? Put S equal to alpha. How much it will be? K by 2. And it is independent of R2 dashed. In other words, we can say that the maximum value of torque developed by the induction motor is independent of the value of the rotor resistance. It does not depend on that. However, rotor resistance will decide at what point on the slip axis that T max will occur, because R2 dashed by X2 dashed is that slip, is not. Now I will tell you some of the things about the torque slip characteristics. you remember that so far we are discussing about the what type of induction motor? We are discussing slip ring induction motor. Or they are also called wound rotor induction motor. As you know, in such motors the rotor terminals are available through slip ring and brushes for external connection. Now suppose we will now examine if certain parameters of the rotor on the rotor side are varied, how the torque slip characteristics gets modified. Okay, that is what we are going to study. That is, if this is your induction motor stator. This is the rotor. These are the slip rings. And these are the fixed brushes. Now, one of the parameters which are varied in the rotor circuit is the rotor resistance. This I can easily manipulate by connecting 3 external resistance in the rotor circuit. Okay, suppose R2 dashed is the winding rotor resistance per phase. Winding rotor resistance per phase. Refer to, of course, stator. Refer to stator. Suppose R external is the actual external resistance connected on the rotor side per phase. Per phase external resistance connected in the rotor. Are you getting? Therefore, what is the actual rotor resistance per phase? It is R2 plus R external. This way I have changed. Is not? See, actual rotor resistance per phase then becomes rotor resistance, total rotor resistance per phase becomes this one. Now, if I do like that, what happens to the torque slip characteristics that we want to study? Let us see. We know let when R external is equal to 0, then R2 was equal to R2 only, rotor resistance. And what was the torque slip characteristics? Let us plot it. This is S equal to 1, this is S equal to 0, and to this curve we write total rotor resistance. R2 is R2, actual resistance. Now suppose the rotor resistance is increased per phase value, and this is the value of the maximum torque, T max. Suppose I have increased the rotor resistance per phase. Do you think this maximum torque, wherever it occurs, will it change? No, because it is independent of rotor resistance. So I draw a line here, and I know that the maximum torque point will lie somewhere here. Now the slip at which maximum torque occurs, does that change? Yes, that will change, because initially it was, suppose, let me write, it was S1 max at which T max occurs. So what was S1 max? it was equal to R2 by X2, is not? Dash torque, this value is same because that turn square will cancel out. This is same as R2 dashed by X2 dashed. You are taking ratios. Okay, are you getting? R2 by X2 is R2 dashed by X2 dashed. Now, suppose rotor resistance is increased to R2 plus R external, and then the slip at which maximum torque will occur, let us call it S2 max, it will be equal to, definitely R2 was there, plus R external I have added per phase in the rotor circuit, divided by X2. Leakage reactance I have not changed. So it will be like this. Obviously, this slip at which maximum torque will occur will lie towards the right now, which is greater than S1 max. Suppose this is the value of S2 max on the right of S1 max. Then what will be the, so at this point if you draw a vertical line, you know Tmax point of the new torque slip characteristics has to lie there. Therefore, its shape will be now like this. Okay, the slip at which maximum torque occurs has shifted towards right. So this is suppose external R external 1, in this way I have connected. So this curve corresponds to R2 is equal to, I mean new R2, that is R2 plus R external. This is the rotor resistance corresponding to this, it is this. In this way, you can imagine that if I go on increasing the rotor resistance, R external as a parameter, this curves will further shift to the right. I can further shift it to the right by simply increasing the rotor value of resistance. Do you think it can help me in any way? What do you observe? Starting torque increases. The value of the starting torque increases. In fact, one can choose some optimum value of R external such that the whatever maximum torque the machine can develop, that will appear during starting. That is, you choose your R resistance, external resistance, in such a way that your maximum torque occurs right at S equal to 1. See, simply by connecting resistance in the rotor circuit. So this curve from left to right, if I draw it, you remember this is R2 increasing, R external increasing, increasing. Of course, further increment in R2 dash will reduce, once again start reducing the value of the starting torque, because this point will lie somewhere here where machine cannot operate. So this is perhaps the optimum value of starting torque, I mean maximum value of starting torque one can choose. So what I mean to say, see, slip ring induction motor, therefore, if you want to get a larger starting torque, you can incorporate some resistance connected in the rotor circuit, start the machine, then will you leave the resistance in the circuit? I mean, what I mean to say, suppose the problem is like this, that suppose you have got the inherent torque slip characteristics of the machine, that is the slip S equal to 0, and this is suppose with no external resistance connected. This is suppose the torque slip characteristics of the machine. This is S equal to 1, standstill condition. This is with R external equal to 0. No rotor resistance is connected. Now suppose the machine has to start against full load torque already present on the shaft of the machine, and it is like this. T full load, as I told you, it will come in midway in this curve about. So suppose this is the T full load torque. And suppose you are going to start the induction motor in the normal way. Rotor short circuited, give supply to the stator winding. Then what will be the thing? In this case, can machine start? It cannot, because electromagnetic torque developed is much less than the torque to be overcome by the machine. Therefore, machine will fail to start. So, in such cases, what you will do now? You, instead of keeping the rotor shorted, you connect some external resistance in the rotor, equal values in all the phases. That's why gang resistance I showed in the external. So equal values you connect, like your 40 ohm gang rheostat, 3 you use, connect them. And you modify the torque slip curve such that suppose this value you choose. Some R external you connect so that the torque slip characteristics is shifted towards right in this fashion, such that the starting torque now will be this much, full load torque is this much, machine will start. Now the point is, suppose I keep that resistance in the circuit, I don't bother, machine is started, fine. Where the machine will settle down? Where machine, which will be the operating point of the machine if you don't do anything with R external now? It will be here. Because this is the torque slip curve prevailing in the machine now, dictated by the present value of rotor resistance per phase, which I have increased and did not bother to cut it out. It was there in the circuit. So this is, as I told you, it is R2 plus some R external is there. Okay. Do you think should I leave it like that? In that case, there will be unnecessary copper loss taking place in the machine. And machine will, of course, will run at this speed like that. But power loss will be taking place. So, as the machine now picks up speed, then like your DC motor, what do? You cut out that resistance. So, as the machine picks up speed, you cut out that resistance. This Tmax level is same here. You go on, cut out that resistance gradually and bring it to 0. So, what you have exploited? You have exploited, machine will operate with its own resistance ultimately. But initially you faced one difficulty, machine cannot start. Because the torque against which it has to start is more than the torque it can develop. So, for that you incorporate some resistance in the circuit. As machine picks up speed, you gradually cut it out. So, operating point will shift in this way. Suppose it starts here, operating point moves along this curve, no doubt. Okay, now what do? You cut out those resistance further. Suppose this is the another torque slip curve. So it moves like this. It comes here. Suppose at this point you switch over to this curve, then it will go there, come there, and ultimately here, when all external resistance is shorted. Are you getting? Well, no, what I am trying to tell, suppose machine is moving like this, it is the curve, okay? Suppose at this point some R external is changed, reduced. So the point of operation at that point of time, what will be the torque slip characteristics? Machine will refer to this. So point of operation will come here, then it will move. The way you change it. Is that clear? So, of course, we are interested in the final operating point. It will come nicely here. Okay, of course, we will be doing there it continuously, R external changing. But to understand what is really happening, okay, R external 10 ohm was there. Now it is suddenly made 8 ohm. Then corresponding to 8 ohm, the characteristic itself is changed. And the slip cannot change instantaneously like that. The point of operation will jump from one characteristics to another and will move along that characteristic so long you are not once again varying that resistance. Like that it will go and finally settle here. Therefore, we find that rotor resistance helps you to improve the starting torque of the machine. And of course, it helps you in another way that we will discuss in great length, but you can easily understand the current drawn during starting will be also reduced. See, what is the equivalent circuit with no external resistance connected in the machine? It is X2 dashed during starting. It is R2 dashed in a normal machine, no external resistance connected. S equal to 1 during starting, say at starting. And this is the voltage. So current drawn will be V1 divided by this impedance at S equal to 1. Now, what I am trying to tell that this is X2 dashed. You have connected some external resistance now, such that it has become R2 dash plus R external dashed. And same voltage, full voltage is applied. Then how much will be the current drawn? It will be less, because impedance in the circuit has been increased. Is not? But starting current is reduced, no doubt, but starting torque is increased. Is it not a contradiction? Because torque is BIL. How, suppose current is decreased, how can torque increase? It is okay, mathematically we have got all these things. Suppose, no, that is okay in terms of this current we are thinking, na? In terms of equivalent circuit. That is okay, those equations, equivalent circuit, all these things. After all, it is a machine, there is conductor current and it is placed in a magnetic field. BIL something will decide the torque also. Is not? That you think. I will not tell you the answer today. Huh? Because what really has happened, current is decreased, but torque is increased. Why it so happens? You think about it. Huh? Think. Now, anyway, so there is some good points about connecting external resistance. Of course, one should not keep the external resistance connected all the time. Then there will be unnecessary power loss and machine speed will be also lower. Okay. Now, another thing I will tell you that suppose, so this is the rotor resistance variation we have studied. Suppose how torque slip characteristics gets modified if supply voltage changes. Suppose supply voltage I am varying. How this torque slip characteristics will change. So to do that, once again we resort to that approximate expression for the torque, which is K S alpha by S squared plus alpha squared. What is K? K is 3V1 squared by 2 pi ns into there is x2 dash into S alpha by S squared plus alpha squared. So in this case, we are not changing alpha. Alpha is R2 dashed by X2 dashed. So alpha is constant. Only V1 is the thing I am trying to vary. V1 is varied. Applied voltage to the stator is varied. Then how the torque slip characteristics will change? Suppose this is the torque slip characteristics corresponding to V1 is equal to V rated per phase. Suppose the applied voltage is 70% of the rated voltage. Then how do you think these torque slip characteristics will change? Do you think the slip at which maximum torque occurs, will that change? No, it will occur at the same point. But what will happen to the maximum value of the torque? That will change. So T max, it depends on this 3V1 square by 2 pi ns into x2 dashed into 2, that is 4. So if V1 is made 70%, so what will happen to T max? It will become 0.49 now. Or in other words, if the applied voltage is changed to half the rated value, it will become 1/4. Are you getting? So this is V1 rated. So if this is 1, so this is say 1/4. All other ordinates will get changed accordingly. So this one is if this is this corresponds to, suppose V1 is equal to half V rated, what I want to tell, and this maximum value of the torque will be only 25% that of the T max here. This will be 0.25 T max. So this will be the torque slip characteristics. One can draw a family of torque slip curve for different rated voltage like this. Is not? All of you have done some basic experiment on induction motor. Tell me, how did you start that induction motor? While starting, did you apply full voltage? You applied from 0 voltage with the help of a variac and went up to the rated voltage. Is not? You must have noticed that if you connect induction motor, this you just listen what I am trying to tell. This suppose your variac voltage, and this is your induction motor stator, 3 terminals are coming out. You give supply. No, that is what you are doing. Suppose from 0 voltage you are increasing the value. So machine will slowly pick up speed. And suppose on the shaft there was no load. On no load you started the machine. Therefore machine speed will rise. No. And suppose the rated voltage of the machine was 400 volt. Even if you apply say 180 or 200 volt, you will find machine is running almost at the very close to synchronous speed. Are you getting? Suppose the rated voltage of the machine is 400 volt. You will observe, even if you apply say 150 volt or so, not rated voltage you have applied, machine is running very close to synchronous speed. This should not surprise us because of the fact that the frictional torque present on the shaft of the machine may be quite low, like this. So no matter whether the voltage is rated, whether the voltage is half this value, the speed variation of these two is quite small. Are you getting? Suppose it is a 4-pole machine. What is this level? 1500 RPM. What is this one? 0 RPM in terms of RPM. So what is the variation of speed here? Corresponding to, suppose full voltage is applied, machine is running, what will be the no load speed? This one. Suppose half voltage is applied, no load speed will be this much. Only little variation. It is difficult to distinguish between these two. what all I am trying to tell is that one should not be under the impression that 180 volt it is running very close to synchronous speed, let us not further increase the voltage, something like that. Because one may be misunderstood in this way that okay, machine is running very close to 1500 rpm, stop increasing voltage, now start loading the machine, like that. What do you foresee then will happen? Suppose then the pull-out torque is so small, that is, you apply this is the corresponding to the rated voltage, and you apply only 25% of the voltage like this, I mean something like this. But the pull-out torque is this much only. The moment you now start loading on this machine where applied voltage is only 50%, that of the rated voltage, then when you come to full load torque, which will be generally midway, as I told you, 5% slip like that, then machine will come to stop, because full load torque is always greater than the torque developed by the machine. So you apply always full voltage. Don't get disturbed by the fact that machine is already running at rated speed, or what will become speed if I apply full voltage. You need not worry, because you know the speed cannot cross synchronous, and at the same time we can easily logically show that the variation of speed from this value to that value is quite small. So voltage change will make the torque slip characteristics move in this particular way. Now, so far so, I will just introduce today with you about something about the cage induction motor. Cage induction motor. And we will refer once again to these characteristics of a cage induction motor. Induction motor. Now, it is the constructional difference in the rotor which makes two kinds of machine. One is slip ring, another is cage. As I told you, in slip ring induction motor, stator houses a balanced three-phase winding. Rotor, two houses a similar kind of balanced three-phase winding in the rotor slots. In case of cage induction motor, stator houses a balanced three-phase winding in the just like that of slip ring induction machine, balanced three-phase winding, no difference, three-phase winding. Stator houses a balanced three-phase winding, like same as like slip ring machine, But rotor is different. That is what I am trying to tell. First, I will tell you how it looks like. See, it looks like this way. I will draw here. Suppose this is the rotor slots, where slots are there, all along the periphery. And this machine, as you know, has got a length. I mean, in 3 dimensions, although it may not look nice, but I will try. So these are the slots. So all along the periphery it is there. I am not drawing. This is the rotor structure. Now what is done is this: you imagine in each slot solid conductor is inserted, say aluminum or copper bar. Not in the form of flexible copper wire, you make the winding not like that. You imagine that this one is a aluminum bar. You just insert in this slot here. Okay. So each slot is filled by a sort of aluminum conductor or copper conductor all along the length. Straight away you put. Such that at both the ends, these two ends are a little bit protruded. That is, apart from this length, they are extended a bit. So in this way, each slot will be filled up by conductors. So I am only drawing the conductors now. In each slot, like this, there will be conductor here. also here there will be a conductor. There also. This goes on like this, all along the length of the machine. They will be here. Okay. That is the structure. If you look from this end, it will cylindrical structure. It is easy to draw in this way that there are conductor bars. From this to this, from this to this. I think you have got the idea what I want to say. And this extended ends of these conductors, they are shorted by the two end rings. You take two copper rings or aluminium rings, continuous ring. Continuous ring means there should be holes so that you can insert that ring in each of the conductors, such that all the ends, free ends of the conductors are shorted, as if by wires you have joined all these ends here. Similarly, on this side, all these conductors will be joined. Therefore, the rotor consists of several rotor bars which run along the length, and both the ends they are shorted by two rings called end rings. So, next class I will continue with this. Stop here today. So, all of you can collect your laboratory notebook from Mr. Kaushik Mukherjee. Whoever has left laboratory notebook, you can collect. That is, he told me to collect.